Hello, and continuing on with Lesson 2, this is Part 3, and in particular this will be associated or focused on the fluid property called surface tension and a couple other important fluid properties, namely the elasticity. Surface tension, I have it on the textbook page here that's relevant to surface tension. And we experience in our daily lives with wicking. If we use a paper towel to pick up water, it'll soak into the water and it's pulled in under the force of surface tension, also called capillarity. There's capillary rise. Water will rise in soil. It'll rise in a little capillary tube when they punch your finger and stick that little teeny glass tube in it to suck some blood out of you. Few other things. And then detergent is a chemical additive that we put into water in part because it dramatically changes that surface tension so that this water can get into the pores of fabric as described here. Okay, so we're continuing on Lesson 2, Part 3. And namely it's going to be surface tension and elasticity. Let's deal with elasticity first. So elasticity that you had back in your solids mechanics classes is the amount of volume deformation for a given change in applied pressure. Sometimes it's called the modulus of compressibility or the modulus of elasticity. And in the case of elasticity, the extensive property, elasticity is equal to change in pressure with change in volume multiplied by the reference volume. This is the extensive property. And the intensive property, for lack of better alphabet, change in pressure, change in density, so starting with a reference pressure, if we apply reference volume, if we apply pressure, let's say we go from 1 atmosphere to 10,000 atmospheres, we expect stuff to get crushed. So the change in pressure and change in volume is negative, meaning that it will get smaller. And the elasticity, or the modulus of compressibility, is this value here. Same thing for the intensive property if you do it per unit mass. This will play an important role in compressible fluids and a lesser role in incompressible fluids. All fluids are compressible. It's just the impact or the modulus elasticity for things like water is such that it takes an enormous pressure to cause any sort of volume change. Whereas things like gas, it doesn't take much of a pressure increase at all to cause a volume change. Now, surface tension. Surface tension is the work required per unit area to separate two fluids. The usual symbol is sigma, and it's usually measured with a ring tensiometer. If you look at problem 2.67, you'll see an example. In fact, we will go ahead and do that right now. There we go. So here is a elevation view of a ring tensiometer. So imagine looking down on this. If you're a seagull looking here to try to get your poop right in the middle of the ring. It has a diameter and a force is applied, and it tries to lift the ring out of the liquid. And then the amount of force it takes to pull the ring from the liquid, divided by the area of the ring is defined as the surface tension. So dimensionally, surface tension has dimensions of force per unit length. Okay, so dimensionally, is force over length is the dimensions of tension. Surface tension is the main reason why liquids can rise up in capillary tubes of porous materials. So surface tension determines the contact angle between phases. And we'll go ahead and look at a common three-phase system. Let's look at the one that is built on your automobile. We take a drop of water and we hit it on this glass, and we have an air, glass, water system. In this case, the contact angle theta is less than pi over 2. This is the water is a wetting fluid. And actually it's quite easy to tell where wetting fluids are because they chisel into the non-wetting fluid. In this case, air is non-wetting. Now we're going to take that same same situation. We're going to use purple wax. Purple wax, purple wax. I don't think Pitchfork would mind that. The reason we put wax on the glass of our windshields is to cause the water to bead up on it. And in this case, a drop of water does that. And if we look at the contact angle, we have theta is now greater than pi over 2. Water is non-wetting. So the surface tension largely controls whether the liquids will spread out or bead up on a system as described here. The wetting properties are certainly important. If we apply a detergent to the water, then that can change its surface tension and change its properties. I don't know if it's possible to add enough detergent to water to get it to spread on the wax, but given that detergent is used to remove wax, I would guess that it is possible. So capillary rise is related to wetting. And capillary rise is the tendency of a liquid to rise up in narrow tubes. It's how absorbents, such as paper towels or canape for fuel spills, work. And it can be explained using a simple force balance. And so we will go ahead and do that. We'll assume that we have a reservoir here of, let's make it water. Good water, nice and blue. And we're going to use a relatively small diameter tube. And the water will rise up into some height. Or we can do this in a straw. So this could be glass. Here we have air. And here we have a tube of diameter D. And the height and rise maybe from this surface. And I'm trying to get the bottom of that. Okay, so if we were to do a free body diagram of the portion of water that's in the tube, we would use our magnifying glass, an eyeball there, and we would look through and see this. There's the water in the tube, units in diameter, and roughly 8 units tall. And we'll have a R-axis and a Z-axis. And if we were to examine the free body diagram, whatever the mass in that column of water is has a weight. And the only thing keeping the water from sliding back down is this tension force which wraps around the circular interface. And there is a known angle here, alpha, which looks like a fish. Okay, that's a little bit more clear. I'm glad I looked at the video. So there's our free body diagram that we want to analyze. So if we're to write a force balance, we're going to take this force, F sigma is equal to sigma times length. We're going back to the dimensionality of surface tension. F over L is tension. Therefore, sigma times L is the equivalent force. And that's equal to the surface tension. And now we have to figure out this length. Well, it's the length of the circumference, which happens to be pi times the diameter. But that force is pulling both in the radial and in the z direction. And the part that matters is what's in the z direction. That's what's holding the water up. So if we look at the sum of the forces in the z direction, mass times acceleration, z acceleration is 0. We have F sigma sine alpha minus W equals 0. Therefore, we will replace F sigma with sigma pi times the diameter, times the sine of alpha, equals, and now we need to express the weight. Well, the weight of the water, a good approximation is pi d squared over 4. That's the area of the circular cylinder multiplied by its height h, which we can draw h right here, multiplied by the specific weight of water. This whole thing here is the weight of the water column. And, we're ignoring the little triangular part, so that's not going to play that big a role. And if we solve for h, we come up with h is equal to 4 sigma sine alpha over rho g times the diameter. This is a useful formula for estimating capillary rise based on knowledge of the surface tension and the diameter of the capillary tube, and to some extent whether or not it's a wetting fluid. Observe that for water, the contact angle is nearly pi over 2. Then the sine of pi over 2 is essentially 1. And so for water, the water glass system, h is pretty close to 4 sigma over rho g d. All right, well, let's apply that. So imagine, if you will, we want to find capillary rise for water in a glass tube. The diameter equals 1.6 millimeters at 20 degrees Celsius. Okay, we could make a sketch. So we want to list our knowns. We know the temperature, 20 degrees Celsius. We know the diameter, 1.6 millimeters. We know it's a water-air glass. Unknown is H, governing equation. H 4 sigma over rho g d. Solution. Well, first we want to look up sigma at 20 degrees C, and on the offhand it's available, let's look up at rho g at 20 degrees C, and this will give us a chance to use some of our other. So if we go to the mighty internet, the primary toolkit looks like it's up and running. We'll know in a second. We want to get the properties of water at 20 degrees Celsius with the humidifier. And we have the specific weight is 9790 cube, and unfortunately it does not appear to have the surface tension. That's a weakness. So we will go back to the readings and see if we can find that. All right, we're looking for surface tension. Is it air? Common liquids. All right, well that's interesting. The mighty GoogleNet, it claims that water air is, let's see, 72.86 millinewtons per meter, so that would be 0.0728 newtons per meter. And I've written the two values that we've gotten down, where we looked up these, and now we can apply. So this was an internet lookup. This is an online table. Same as table in the back of the book. And now we can go ahead and perform the indicated arithmetic. We have H equals 4 times 0.0728 newtons per meter. Divide by 9790 newtons per meter cubed, multiplied by our diameter, which is 1.6 millimeters, which is 0.0016 meters. And the arithmetic of that I cannot do in my head, but we can use a gonculator. Gonculator. You'd think I would have that in the toolbox, but I guess not. There's the gonculator. Okay. 4 times 0.0728 times 1 divided by 9790 divided by 0.0016 equals 0.01859. 0.01859 meters, which is 18.6 millimeters. There's our answer. Simplify that. And that is an application of surface tension. Okay, so to summarize Lesson 2, and to a lesser extent Lesson 1, what we've basically done in Chapters 1 and 2 is we've defined the fluid. We discussed continuum in particular, particle concepts briefly, dimensions and units, unit conversions, within the grid system, foot, 3.28 feet per 1 meter,
that's all I give you your conversion. I give you your XT. So make sure that 3.2 equation of state for gases. We didn't discuss much about dimensional homogeneity, although I certainly alluded to it in the various examples. Fluid properties. Extensive and intensive. Density. And viscosity. Viscosity, as we call how equal to mu, dV, dy, Newtonian, and then mu becomes an apparent viscosity phenomenon. That's pretty much chapters 1 and 2 to Civil Engineering 3305. Thank you for your attention. And that concludes this part 3 video for lesson number 2.